Today I want to talk about how we can use physics to perform simple mathematical computations, such as addition or multiplication. But at first, why would we want to do that at all? Well, when we perform, let's say, addition, right, we might write something like 14 plus 27, and we usually have some sort of procedure of how to do that, right? We might add 4 and 7 to get 1 and 1 carry, and then we add 1 and 2 and 1 carry to get 4, which gives us in the end that the sum of these two numbers is 41. And this is a simple calculation, and it took me some time. But of course, to save time, I could maybe use a computer, because they are great at these kinds of computations. They're very fast at it. If we look at this logic circuit here, it's a circuit that performs addition. It might look like nothing that you do when you add two numbers, but it actually uses some of the same principles that we use every day when we add two numbers together. There are concepts like adding digits, adding carries, and so on. But even computers, when they have to deal with millions or billions of numbers that they have to add or multiply, it can take them some time. And to add to that, there is the issue of energy consumption. If we have a lot of calculations, then of course we are going to consume a lot of power. And I want to explore whether we could somehow use the physical world to perform some of the computations that we care about for us. And how can we actually do that? If you look at the physical world, it is governed by equations. We might have planets that follow laws of gravitation, right? There are equations that govern their motion. And in a way, their movement is a representation of these laws. Essentially, by observing these bodies, we can also deduce something about the computations that are going on. Of course, these bodies are not consciously computing anything, but their motion is indicative of some of the calculations that are going on underneath. The question is, can we somehow utilize this to perform computations that we care about? And of course, that's not very trivial. The universe cannot just spit out numbers to us. It doesn't talk in the same language that we do. So we might need maybe some instruments to extract information from our environment, and maybe we might have to influence the environment to make it do the calculations that we want it to do. So we might have to do some intervention into the environment or some devices that we construct ourselves. So let me start with a simple example of, let's say, a scale, which we can use to weigh things. Okay, so this thing is gonna give me the mass of the objects that are put in here. Okay, it might be like 0 kilograms, 1, 2, 3, 4, 5, 6, 7, and so on. Let's say I don't know how to add numbers, but I see two weights. One of them has 2 kilograms written on it. So I put it on the scale. And then I see another weight. And 1 kilogram is written on it. Okay, so we have two weights with different masses, 2 kilograms and 1 kilogram. I don't know how to add 2 and 1, but the scale says that the total mass here is 3 kilograms. Now, by combining what I know about how masses can be combined in the physical world, I can deduce that 2 plus 1 is equal to 3. Now, I know what you're thinking. This is the stupidest example ever, right? I mean, we can't really use that in practice. Just imagine an accounting department having thousands of different weights for all the different combinations of sums they would need to compute. So that's kind of stupid. But it might illustrate a point. So this approach is not scalable. Let's see if we can come up with something better. Let's come up with an example where we can control the variables in a more convenient way, without, let's say, coming up with new objects that we have to weigh on a scale or something like that. So what we might have is maybe, let's say, wires, metallic wires, 3 metallic wires that meet at a junction, and then we have 1 wire on the right here. And let's say what we can do is we can pass certain amounts of current through each of these wires on the left. Let's say I1, the current I1 is equal to 3 amps. Okay, and current is essentially a measure of how much charge is flowing through a wire. Okay, so let's say we can influence how much current we pass through each of these wires on the left. Let's say I2 is maybe 4 amps. And then I3 is equal to 2 amps. Okay, so amps are the units of current. And now there is this idea in electronics which is called Kirchhoff's current law, or KCL. And I think I definitely made a mistake in this guy's name. Anyway, what this law says is that the currents coming into the junction, their sum must be equal to the current going out of the junction, or the sum of currents going out of the junction. So by this, let's name it I, should be equal to I1 plus I2 plus I3 by Kirchhoff's current law. Now, why is that the case? Well, I mentioned that current is a measure of how much charge is flowing through a wire. So charges are these, can be some sort of particles. And of course, in reality, they usually flow in the opposite direction, but the principle is kind of the same. You have some charged particles that flow in one direction, and if they meet at some junction, whatever comes into that junction must come out. Okay, so if we have 3 currents, I1, I2, I3, coming into this junction, these same currents must also come out. That's essentially the conservation of charge. We cannot destroy or create charge. So this has to remain constant, which is why we have this I here on the right equal to the sum of these free currents on the left. Now, suppose once again that we don't know how to add numbers ourselves. Okay? What we might do is we might attach some sort of device that measures the current on the right. And let's say what it tells us is that that current is equal to 9 amps. Now, what this also tells us is that this thing here is equal to 9 amps. Okay, that's the current. And we know that this should be equal to the sum of these three currents. Or if we kind of translate this to arithmetic, which we care about, right? That's why we are doing this in the first place. We can say that 3 plus 4 plus 2 is equal to 9. Even though we don't know how to add numbers ourselves, according to these physical laws, we know that this sum on the left should be equal to 9. So that's how we can perform addition using electric circuits. And this seems kind of strange. We are doing a lot of work here to perform this very simple calculation. We have to encode these numbers 3, 4, and 2 into the currents. Then we have to construct the circuit. Then we have to add a measuring device to measure the current that is going out of the junction. And only then do we get the answer to our simple problem, our simple question. So it's really questionable if this is a feasible approach, which means that we have to think about whether we can apply it in some certain applications. Before we do that, we might want to think about some other simple operations that we could maybe implement using physics or maybe using electric circuits. And one that comes to my mind is multiplication, which is a very useful computation, very useful operation. So let's say we have a resistor. Resistor is an electrical element which resists the flow of current. It is characterized by resistance, R. The larger this resistance, the smaller the current flowing through the element. And the smaller the resistance, the larger the current. If we attach a battery, let's say, if we attach a battery to this thing, the battery, you might know, if you ever looked at one, is characterized by a voltage or a potential difference that it can produce when we attach it to some external element. And we denote voltage by the letter V. Okay, and this, of course, resistance. So now if we attach a battery with voltage V across this resistor, we have a law called Ohm's law. Which tells us how much current we should expect to be flowing through this resistor. It says that the current I flowing through the resistor around this circuit is gonna be equal to the voltage V divided by the resistance R. So that's kind of interesting. Because what we might do now is we might be able to actually perform division using Ohm's law. How can we do that? Well, we might, although it's not very convenient, we might choose the right kind of battery with voltage with V that we are interested in. For example, we could choose V equal to maybe 3 volts. Okay? And we might choose a resistor that we care about. Let's say 2 ohms. Resistance is equal to 2 ohms. Okay? And if we do that, then we know that the current flowing through this resistor is going to be 3 volts over 2 ohms, which is going to be 1.5 amps. Okay? So now I did this mentally because I know what 3 over 2 is. Okay, but suppose I didn't. I could have measured this using, again, a device that measures current. And I might have extracted this value from here, 1.5 amps. And then I would have deduced that 3 over 2 is equal to 1.5. Now that's kind of useful, but I promise you that we could also do multiplication in this way. And the way we do that is kind of like a very simple trick. What we do is we introduce a new kind of variable called conductance. Conductance, which I'm going to denote by the letter G. And we are going to define. Okay, so this means definition. We're going to define this as being equal to 1 over R, the reciprocal of the resistance. Now, if we do that, I can actually rewrite this thing here. I can rewrite this in the following way. I can write V times G. And now you probably see where this is going. Okay? So, if my resistance is 2 ohms, it means my conductance is 0.5 Siemens. Siemens is the unit for conductance. What this means is that I could think of the current as being equal to the product of 3 volts and 0.5 Siemens. Let's say I don't know how to multiply 3 and 0.5. Well, what I could do is pick a resistor whose conductance is equal to 0.5 and pick a battery that has a voltage of 3 volts. Okay? And this would give me the current of 1.5 amps, which means I can then deduce that what we have is essentially that 3 times 0.5 is equal to 1.5, just by using Ohm's law. But once again, this doesn't seem very feasible. We have to do a lot of actions to perform very simple operations. We have to pick a battery, we have to pick a resistor, we have to have a measuring device for the current. It's way too much work for the simple calculations like these. So the next question is whether there are situations where we might combine these simple implementations of these operations like addition or multiplication in contexts where we have much greater computing requirements, where we have many more additions and many more multiplications? And the answer might be yes. We might want to look at the concept of vector matrix multiplications. And these words might look scary to you, but do not be afraid. These are very simple concepts. Oops, what am I doing? Vector matrix multiplication. So what are vectors and what are matrices? You can think of these as sets of numbers, groups of numbers. I'm trying to be careful to not use math terminology that applies somewhere else, but you can think of these as tables, maybe tables of numbers. You could have numbers like maybe, I don't know, 2, 3, and 4, like a row of numbers. That's a vector. That's a vector. And you could have a table which has both rows and columns. You might have something like 1, 6, 5, 2, 2, 4. And here we have 3 rows and 2 columns. That's a matrix. Now, there are lots of data for which this kind of representation is useful. Columns might, for example, represent different days, and the rows might be different temperatures. So, if you look at any row and column, you can find the temperature on a given day or something like that. So in some scenarios, it's a useful way to represent information. And when we deal with these types of structures, we often find that there are some useful operations that we usually utilize, and we make up some new operations and give them names. So vector matrix multiplication is one of these things. It's called multiplication, but we also perform a lot of addition in there. So it's really just a name and just a definition, and you don't really need to know how to perform it at all. Okay, but I just want to give you a definition so that we can have a common language and understand this is something that can be useful to compute in some contexts. For example, in statistics or machine learning, although they're essentially the same thing. And we might have some numbers, so I'm just trying to reproduce here the same vector matrix here to kind of give you a sense of how do we perform vector matrix multiplication. Okay, so if we have something like that, if we put them next to each other, it's a bit like, putting 2 numbers next to each other. It usually denotes multiplication. So how is this thing defined? Well, it's a very mechanical procedure. What we do is we firstly take this row and kind of multiply it by this column. Now let me show you what I mean by that. So we have A, B, C, and then I have D, F, and H. You see this first column here. And then I add those 3 products. That is going to be my first element of this product. And then the second element is going to be produced in a very similar way. We're still going to take this row, but we're going to multiply it by this second column now. So it's going to look like this. We're going to have A, B, C, and then here we're going to multiply these by respectively E, G, and I. And then finally, we are going to add them together. Okay, so by this logic, the way we would compute this thing right here, we would do 2 times 1 plus 3 times 5 plus 4 times 2. So that's for the first element. And then for the second element, we're going to have 2 times 6 plus 3 times 2 plus 4 times 4. Okay, and we can actually compute what these are equal to in this specific case. So this first one is 2 plus 15 plus 8. So that's, I think, 25. And then for the second element, we're going to have 12 plus 6, which is 18, plus 16, which is 34. So what we get is essentially a row vector with 2 elements. And you don't need to understand why this is useful, but let's just say this is an operation that a lot of people in science, in finance use, and that's what we utilize our computers for all the time. And it takes some time to compute these things because, as you can see, there are a lot of operations that are going on here. We have multiplications, we have additions, and you can imagine that if we have matrices that are millions of rows in size, it can take some time. So the question is, can we somehow accelerate these sorts of operations? So let's have a look at how we could actually do that. And now I'm going to draw a circuit that is not going to make sense at first. So trust me for a moment, and we're going to see why I did what I did here. Okay, so I'm going to have essentially 6 resistors drawn like this in the shape of the matrix that I used in the previous page. Okay, I mean that I'm going to have 3 rows and 2 columns, like in the matrix here. So let me do that. And I'm going to do some resistors here. And one more. So what I'm going to do is I'm going to choose these resistors to have the same values numerically in terms of conductance as the matrix in the previous page. I'm going to give this resistor a conductance of 1 Siemens, this one of 6, this one of 5, this one of 2, this one of 2 as well, and this one of 4 Siemens. Now, what I'm going to do next is connect them in a very special way. So here's what I'm going to do. I'm going to do the following. Okay, so I'm going to connect them in this way right here. And it might not make much sense now, but you'll see in a moment why am I doing what I'm doing. Okay, and I'm going to do the same thing here. So now the first thing I'm going to do is I am going to make these parts in the bottom, I'm going to bias them at 0 volts. Okay, so what this is going to mean is that all of these parts, okay, all of these parts here are gonna be equal to 0 volts potential. Okay, because we don't have any resistors in between, all of this 0 volts reaches up to all of these free resistors on the left. And the same is going to happen here because we have this, which also reaches to all of these resistors on the right. Okay, at their right terminal. Why am I doing that? Well, you'll see in a moment. Because the next thing I'm going to do is I'm going to bias the left terminals of these resistors at a different voltage. So what I'm going to do is I'm going to have something like this. And I'm going to produce slightly different voltages here. What I'm going to do is I'm going to set this thing at 2 volts, this thing at 3 volts, and this thing at 4 volts. And if you remember, these are actually the numbers of the row vector that I had here. Now, of course, this was a row vector, but physically, I'm kind of putting this vertically. Okay, but it doesn't really make a difference. It's just our notation. And in the circuit, it matters a bit more where we actually apply these voltages. And now, I actually want to apply these same voltages to the elements on the right. So what I'm going to do is I'm just going to extend these wires here to reach them. Okay? So because we don't have any elements in between here, okay, all of these segments here are at 2 volts. Okay? Here we have 0 volts, and so on. Okay? So on the left, for these 2 elements, we have a potential of 2 volts, and on the right of 0 volts. Now, similarly, we're going to have something like this here. Now we have to be careful, and we have to go around this vertical wire to not touch it. So we're going to do that, okay? So now 3 volts reaches both this resistor and this one. And finally, we are going to do a similar thing for the last row. We're going to go here. We are going to go around the vertical wire and finally reach the resistor in the bottom right. Okay, so what does this mean? It means that we now know an exact potential difference across each of these resistors, okay? So for this one, the voltage on the left is 2 volts, okay? The voltage on the right is 0 volts. So the difference across this resistor is 2 volts. The same thing here. Here we have 2 on the left, 0 on the right. The difference between these two, 2 minus 0, is 2. We can apply the same logic here, for example. 4 volts here, 0 volts here. The difference is 4 volts. What this lets us is it lets us to use Ohm's law to compute the amount of current each of these individual resistors produces. Because we know by Ohm's law that the current produced is equal to the product of the voltage across the potential difference across the resistor times its conductance. So that's very useful because now we can find the amount of current each of these ones produces. So this one is going to produce what? Well, it's going to produce 2 times 1, okay, amounts of amps, okay, because we have 2 volts and 1 Siemens. Here we're going to have 2 times 6. Here we are going to have 3 times 5. Here we're going to have 3 times 2. Here we're going to have 4 times 2. And here we're going to have 4 times 4. Now, that's the Ohm's law and the amount of current each of these produces. Now, if you look at this circuit carefully, what we find is that actually these branches on the right meet, okay? So for example, this branch and this branch meet here. And then these two combine, which, they go here. They meet this one and they get combined here. Which means that we can use Kirchhoff's current law. We can use Kirchhoff's current law to compute the total amount of current that is going down the wire at the bottom. What this means is that the current here is going to be the sum of this thing, of this thing, and of this thing. Or 2 times 1 plus 3 times 5 plus 4 times 2. And here we're going to have 2 times 6 plus 3 times 2 plus 4 times 4. And these are actually, I think, the exact numbers that we computed when we were calculating the vector matrix product in the last page. Let's have a look. Yes, I think they are, right? So these are the exact numbers that we were computing. So what this means is that by encoding the vector into the voltages that are applied on the left and the matrix into the conductances of these 6 resistors, we were able to extract the product of this row vector and a matrix by looking at these currents at the bottom, the one here and the one here. They correspond to these 2 elements in the output row vector. So that's a lot more exciting. But let's try to be skeptical here. And let's ask some questions. Is this feasible? It's still a lot of work, right? We are trying to compute vector matrix product, but we still had to set the voltages. We had to pick the right resistors, right? And we had to add some measuring devices to measure these output currents. Now, for the voltages, it might not be that difficult to change them. Okay, there are devices that can apply arbitrary voltages here on the left. But yes, for the resistors, it's a bit more complicated. Okay, it's a lot more complicated because we'd have to pick different resistors each time we want to compute a different vector matrix product. That's kind of complicated because we'd have to essentially fabricate a new version of this circuit each time. Now, we might be able to use maybe memristors, which are devices that have a lot of interesting properties, but one of them is that you can often change their conductance in a relatively easy way. So we might do that, but even then, it's quite a lot of work to do that each time. And the second problem I can think of is that this is not exactly precise, these computations, because we know that, 2 times 6 is 12, right? That's exactly 12. We know that. But is this circuit gonna compute 2 times 6 correctly? Well, not exactly. Can we set this voltage to 2 volts exactly? I don't think so. It might be something like 2.0001 volts, okay? I mean, that's pretty good, but that's not precise. And there are applications where this is not okay. You might do some maybe scientific simulation where this sort of precision is not enough. You might need a lot more of it. But the question is, are there any cases where we can tolerate this kind of uncertainty? And I want to talk about one possible application where both of these problems might be addressed. That is, the fact that we have to change the resistors each time, and the fact that we have some sort of variability, right? So let me just spell out these problems. Changing values of G, so that's problems. And the second problem is precision, right? Can we tolerate some uncertainty? So one application I want to explore is neural networks. What are these? You don't have to understand them in depth, but let's try to get a high level picture of what they do. They're essentially just computing structures that take some input and spit out an output. Okay? We might have some inputs on the left, they go to outputs, and then we might have some outputs on the right. So, for example, we might have a network that takes an image of a cat. That's a cat, if you didn't get that. And if we pass that to the network, if it's a good network, it should give us the answer of what that is. We might have trained the network to distinguish between dogs and cats. And if the network is working well, this output should light up. It should say, I think it's a cat. Now, is this going to work 100% of the time? Definitely not. Even in the real world, okay? If you give me a million images of dogs and cats, even I would not be able to distinguish with 100% accuracy, okay? Maybe there's some cat or dog that I haven't seen before, and I confuse the two. So that's really not realistic, neither for humans nor for machines. What we might have some accuracy like maybe 98% or something like that. So maybe that's more realistic. Now, how do these networks actually work? Now, there are a lot of flavors of neural networks, but almost all of them use one operation, which is called vector matrix multiplication, that we've seen already. Now, they use this operation, and what they do is essentially there are two stages in neural network processing. The first one is training. It produces a set of weights that are essentially unencoded information about the data set, about what makes a cat, or what makes dog a dog. And this is essentially information. And it is encoded into a matrix. Of weights. So we have weights that are produced during this training process. And then we have the second stage, which is called inference, during which we give inputs to the network and we simply expect the correct outputs, or the category of our input, as one example of what a network like this can do. So what this means is that once we train the network, these weights, this matrix, is not going to change. So this thing is going to be constant during inference. What this means is that if we have these vector matrix multiplications that I was talking about, this matrix is going to be constant. And that's kind of good news for us, because if we wish to implement these weights using resistors, what we could do is we could set their conductance to the values we desire once, and we wouldn't have to change these. So it's very useful, okay? Because this matrix is going to be constant. So what is going to change? Well, the vector here that we have, let's say like here on the left, is going to change. And the vector is going to represent the images. Okay, so images are encoded into vectors. So only these are going to change, but that's kind of good news for us because it's much easier for us to change these voltages on the left than it is for us to change the conductances in this matrix. So we kind of addressed one of the problems, okay? Because one of them was changing values of G. That's good news because during training, we get one set of weights, we encode that into the conductances of the array of resistances, of the resistors, and this doesn't change. Now, the second problem was precision. Now, I kind of alluded to the fact that neural networks are not actually perfectly accurate, okay? They will never have 100% accuracy. They might have something like 98% accuracy. And what we find is that when these weights are changed a little bit, or these inputs are changed a little bit, we don't get 0% accuracy. We might have something like an accuracy of maybe 97%. So that is, of course, not ideal. We don't ideally want to decrease our accuracy, but that's not catastrophic, okay? It can still work for most of these examples. And the question is this a good trade-off? Because with circuits like these that we've seen before, these kind of arrays, what we can do is we can save power. So we can save power. They consume much less power and time. So the computing time might decrease. And of course, there are a lot of things to consider, but that's something that we might hope for. So that's a good thing. And of course, the con is that we have decreased accuracy because the precision with which we can program these devices with a certain conductance and the precision of the voltages we can apply, of course, is not as good as dealing with digital logic with transistors in modern computers. So this is a trade-off that we have to think about if we want to use these kinds of circuits for computations like vector matrix multiplications. So as you've seen, these kinds of implementations, that is using physics to compute even simple things like addition or multiplication, it's not trivial. Not trivial. There are a lot of things to consider, and I haven't mentioned even most of them. So we have a lot of engineering challenges. But if this could work, if we could overcome these challenges, it could have a big impact on computing. Because what we find today is that applications like machine learning are consuming more and more power. You might have seen in the news how large these neural networks are becoming for various tasks that we want to perform. Of course, they are amazing at a lot of tasks, but there is a lot of concern whether we can actually scale these systems and address the power efficiency concerns. So that's a possible option to explore And of course, I'm not saying that this is how we are going to address this very big challenge of power efficiency in machine learning and even in some other areas. But it's one that is quite promising one, and one where a lot of research is taking place. So thank you for watching, and hopefully see you next time.